Good morning, everybody. Hope everybody's doing well. Welcome to Wednesday, I guess. That's where we're at. Just to remind you what we were going through in the past lecture, we just started into a review of trig identities and going through recalling like the Pythagorean identities, half angle or power reduction identities for trig, and then the product of sum formulas, although that last group, the product of sum formulas, are not memorizable, but everything else here definitely you should have already in your head, which is kind of nice because if you think about it, those are the core identities from trigonometry that you have to use all the time anyway, so it's not a huge deal. Then again, last time we reminded ourselves about these integrals, the integral of tangent and the integral of cotangent, and I had mentioned that it's probably a good idea to remember or have the integral of tangent in your brain. If not, you can rederive it pretty quickly. It's just sine over cosine, let u equal the cosine, and you get that. And then this one right here is very, very popular, the integral of secant. That one I definitely would commit to memory because it just happens often enough, and you don't want to have to rederive that all the time. So those two right there, along with maybe the cosecant, I think that's a good one to remember. Although, to be honest with you, the cosecant you rarely run into, but the secant you run into a lot as far as the integral. Let's see, what else did we do? We started into evaluating integrals involving trig functions, powers of trig functions, and I gave a piece of advice, and it looks to me on my end that my screen is lagging slightly, so sorry about that. But I mentioned last class session that a piece of advice would be to, when working with trig functions, to get your goal is to get even powers. You really would love to have even powers because then you can use the Pythagorean identities. It's really the ultimate goal is to use those Pythagorean identities, maybe the half angle identities, but mostly the Pythagorean identities. Essentially, the material in this section is just glorified u substitution. There's no new technique here. It's just u subs. In this first case here, we let u equal the sine. Oops, that's not a pen. This would be a pen. We let u equal sine, and then du stole away a single power off of that cosine, and that left us with an even power on cosine, which allowed us to use a Pythagorean identity. That's the whole idea, right? Then you could exchange that cosine squared for 1 minus sine squared, and then use that substitution for u to now integrate a polynomial. Very, very nice. Just remember when you're doing this stuff, especially with indefinite integrals, in the very end, you want to step out of that world of u and back into the world of x's. So u was sine, so instead of u to the fifth, it's sine to the fifth, and so on and so forth. And then we moved on. I think this was probably the end of the lecture. We moved on to this guy right here, the seventh power of sine. And again, or the integral, the seventh power of sine. And my advice was to force this power to be even, and the way you do that is with an odd substitution. You let u equal something that's not even there, and the reason why is because its derivative will steal away a single power off of that sine, sorry. And so that was the ultimate goal there, is really to, again, remove a power so you get down to even powers. I mentioned off to the right hand side here because I see this every semester. People love to think that integral of anything to a power is going to be that thing to the power over the power plus one, or sorry, that thing to the power plus one over the power plus one. That is not true. That only works if that something was an x. That's the only time you can do that. So please do not use that when you have sine to the seventh or something like that, or natural log to the seventh, or it doesn't really matter to the seventh other than x. Okay. So you could see the whole pattern here is really to remove a power so that you get to even powers. Once we got to an even power on that sine, remember, we had u is equal to the cosine. So I'd like to rewrite that sine to the sixth in terms of cosines, well, that's sine squared to the third. That's what sine to the 6 is. I'd like to reduce that down to a sine squared if I could, because I know that sine squared is 1 minus cosine squared. And cosine, remember, is what we let u equal. And now we're back down to a polynomial. Multiply it out and integrate and resubstitute in the end. There you go. And you guys have actually seen, I've been watching the forums. You guys have already seen that some of the problems are coded with a plus C already built into it, like at the end of the answer box. And then some require you to type in plus C. And then some actually don't accept a plus C for some weird reason. So I'm going through in future homeworks and making sure, if I possibly can, that they all have you type plus C if they're indefinite integrals. I can't guarantee that's going to be the case, but I'm really trying to recode a lot of people's terrible coding where they don't have that plus C. That plus C is a requirement. But if it marks you off, I would then go ahead and try it without the plus C. But any problem that I code will require the plus C if it's an indefinite integral. Otherwise, it's technically incorrect. Anyhow, so today we'll start right back up, and we are going to power through. It's actually just the same stuff over and over again, just different types of substitutions, trying to get powers down to even powers if we can. So taking a look at this guy, the 5th power of tangent. Well, there are a couple things you might want to think about doing. Let me take a drink real quick. All right. One thing, you know that there's 2 ways you can go here, honestly. Let me write down tactics. So one thing that is going to be what I'm going to do is a U sub here. I probably would not write down by parts, although by parts might work nicely. It won't work nicely here, but sometimes it might. But I'm definitely going to use a U substitution, a glorified U substitution here. I just need to write down what are my possible U subs. And our possible U subs would be either U equals a tangent or U equals the secant. Now you could technically rewrite tangent as sine over cosine. So that'd be sine to the 5th over cosine to the 5th. And that's actually a really good choice. That's another good choice. So let me write that over here. I'll say, or tan, are we in X? Yeah. Tan of X is equal to sine of X over cosine of X. And in that case, you can let U equal, remember, this will be sine to the 5th over cosine to the 5th. So in that case, you could actually let U equal cosine. I wouldn't let U equal sine, but I would, in that case, I'd let U equal cosine. And that U equals cosine would steal a power of sine away. In fact, let me go ahead and showcase that down here. You'd have integral of sine to the 5th of X over cosine to the 5th of X. Doing it this way, there's nothing wrong, because if you do the substitution U equals cosine, then du is going to be a negative sine of X dx. It's going to steal away a power off the sines and the dx, and it's going to trade it out for a negative du. That's what this sine of X dx is going to be traded out for. And that, if you did that substitution, really leaves you with a nice integral, actually. So let me go ahead and grab this guy and just say I'm going to do my substitution here. I'll steal 1 power away from the sine. I'll trade it out for a negative du. Okay. And so I'm left with 4 powers on that sine. And downstairs, the cosine to the 5th is actually U to the 5th, because U is cosine. Now, before I continue forward with this, I want to mention these other 2 possible substitutions that I didn't even start into because I just kind of sidetracked myself into working on the one that will work. The other 2, it's not necessarily true that they will not work. It's just that you have to be really creative to deal with the other two. We'll come back to them in a moment, but we're already on this blue ink, so I might as well finish it out. Notice that even power on that sign is very advantageous because you could write that as a sine squared of x squared. And if you've noticed so far, that's really what I try to do. I try to get things down to a sine squared or a cosine squared or tan squared or a secant squared or anything like that, because at that point, I can use a Pythagorean identity. Sine squared is 1 minus the cosine squared. And the cosine, because of our substitution, the cosine is u. So this will be negative integral quantity 1 minus u squared over u to the fifth. What's interesting about going into these integration techniques that we're in right now is that you're going to find that you run into problems where there are several ways you could tackle it. And your answers will look different depending upon how you tackle the problem. So do not get too married to seeing a key and having to match that key. So if you look at the key in, let's say, a book or something like that, that you're working out of, and if the answer key doesn't match your exact answer, that doesn't mean your answer is wrong. It just means they might have integrated a different way. They might have done a different type of substitution. So be very aware of that. I'm going to go ahead and split this into 3 fractions. And I also am going to distribute that negative in just because I have a habit of doing that. So negative u to the negative fifth plus 2u to the negative third minus u. Actually, this one I'm going to write as 1 over u. U to the negative first is a very special one. So I like to write that as 1 over u because the integral of 1 over u is the natural log absolute value of u. And it's just nice to see it that way. All right. Antiderivatives, right? So add 1 to the power, divide by the new power. And I would normally write a negative 4 there, but there was a negative out front. So I'm going to just cancel those negatives. And then plus 2, add 1 to the power, divide by the new power. Again, that negative can go out front, and also the 2's will cancel beautifully. Minus the antiderivative of 1 over u is a natural log absolute value of u, and then you have that constant of integration at the end. And we're not done because we need to figure out, or we need to exchange those variables u for what they should be in terms of x, which is the cosine. So I'll go ahead and give myself even more space, and I'll say that's equal to, you could write as cosine of the negative fourth over 4. I'm actually going to write it as secant to the fourth of x over 4, because that's what 1 over cosine is. It's supposed to be 1 over cosine to the fourth, but that's the same thing as secant to the fourth, minus 1 over cosine squared, which would be secant squared, and then minus the natural log absolute value of the cosine, which technically, if you wanted to, you could use laws of exponents to move, properties of logarithms to move that negative into the exponent to call that a plus natural log of absolute value secant if you want to. And this is what I was saying, that there are alternate forms for all of these answers. Some people might have tangents in their answer. Some people might only have cosines. There's a lot of different ways to write this. So don't get too caught up on, again, matching 100% the answers or the answer key, because yours will be computationally equivalent. Yeah, the natural log part. So another option for this, I'll just say or. This would be plus the natural log of the cosine of x, the absolute value of it, raise the negative first, because you can pull that negative into the exponent. And cosine to the negative first, which is not the inverse cosine, it's 1 over cosine, is the secant. So it's the natural log absolute value of secant. Those are both equivalent forms. They're absolutely correct. All three of these pictures, right here and here and here, are all the same statements. So be very aware, again, that you're going to see answers and you're going to say, wait, mine doesn't look like that. That's right. It probably will not look like an answer that a graduate student wrote someplace else. There's a lot of different ways to write this answer, and some will be so obscure, you'll be like, wait, mine doesn't look anything like that, yet I was marked correct. It's just because of the way somebody integrated. That's all. With trig functions, there's a lot of ways to write your answers, so be hyper aware of that. Now, as far as that tactic, all I did there was exchange the tangent for sines and cosines, but I'm curious if there is another way to do this, just out of curiosity, that's all. So I'm going to go ahead and try a different type of u sub. Let's go ahead and pretend that we let u equal the tangent, because tangent's sitting right here. Why not, right? Let's go ahead and do a second try. So try number 2. It's not really a try when you've already succeeded, right? So our first try, we succeeded. This is try number 1, and we succeeded there. So there's no real reason to do a second version, but why not, right? If we let u equal the tangent, then du is forced to steal away secant squared. And I don't see a secant squared here. And that is why the second try, the way we're going right now, is not super great of an idea, although you might be able to do something with this. Who knows? So let's just try this out. You have the tangent to the 5th, which I'm going to write as tangent to the 3rd times tangent squared. Now, you may wonder why I'm doing that. It's because sometimes with substitutions, it is very powerful to take out a few powers of your tangent. In this case, it's not really going to help out, to be honest with you. If you let u equal tangent, you get u cubed, and I am not going to trade out that tangent squared for a u squared. Instead, I'm going to call that tangent squared secant squared minus 1, because that's a Pythagorean identity. Du is going to steal away a secant squared of x dx. So if you're wondering how I got that, all I did was say, okay, since my picture originally doesn't just have a secant squared dx, maybe I should solve for dx. Dx is equal to du over secant squared. But you'll see right here, we're kind of locked. There's nothing you can do at this point, because secant squared here will not cancel with the secant squared upstairs, because that's locked in an addition or a subtraction. So actually at this point, there's nothing. Well, that's not true. There is something you can do. You can write that secant squared as 1 plus tangent squared. Maybe I'll do that. I'm just curious if that'll work. Secant squared, remember, is 1 plus tangent squared. And actually, since I'm doing that, I'm going to go ahead and just take this secant squared minus 1, which was the same thing as the tangent squared, and I'm just going to call that u to the 5th now. So I'll just I'll glue that stuff back together. And the reason why is because I'm seeing something that is somewhat attractive here. So again, you can ignore my initial split there. I'm going to keep it as tangent to the 5th of x. And if you let u equal tangent, you'll have u to the 5th. And then dx will steal away a du over secant squared, because du is secant squared dx. And you might think all is lost, but you get down to this u cubed over 1 plus tangent squared. But remember what u is equal to. Tangent. So I could then say, well, that's the integral of u cubed over 1 plus u squared du. The problem with this is that this is known as a rational integral, and we don't have a technique yet to tackle this, although you might, that's a big statement, the might there, you might be able to do some manipulations on this. But this is a good example of how you can really go down a rabbit hole when you start doing integrals. You totally can go down a rabbit hole here. I would like to just see how this looks. I'm going to go ahead and continue down this rabbit hole just to showcase. Oh, sorry, that is the fifth power. Thank you. It's because I forgot to apply that fifth power in there. Thank you. So in this case, I may dive further into this rabbit hole. If I do, you might want to do an extra substitution here. You could say, well, what if v is 1 plus u squared? Then dv should steal away a 2u du. It'll steal away a power of u and du. So a single power of u off there and a du, and exchange it for a 1/2 dv. So this will become a 1/2 integral dv. We stole away a single power of u from upstairs, so we have a u to the fourth. And downstairs, we have just a v. Now, this is a mixture of variables, so I'm going to go ahead and move out of this mixture of variables by trying to find a relationship between u and v. Luckily, I have one right here. So I'll say, but, let's see, u squared is equal to v minus 1, which implies, by the way, that u to the fourth is the square of v minus 1, which I'll go ahead and multiply out right now. It's v squared minus 2v plus 1. All right, let's go ahead and do this. This is going to equal 1/2 integral of v squared minus 2v plus 1 all over v dv. And now you can split that apart and integrate this. 1/2 integral v minus 2 plus 1 over v dv. That'll be 1/2 times the antiderivative of v is v squared over 2. So I'm going to actually write that as v squared over 4. Minus 1/2 times 2 is negative. Well, sorry, 1/2 times a negative 2 is a negative 1. Antiderivative would be a negative v. And 1/2 times 1 over v is 1/2 times 1 over v. And the integral of 1/2 times 1 over v is 1/2 natural log absolute value of v. So notice we actually could get to an antiderivative, but we have some resubbing to do. Remember, v is equal to 1 plus u squared. That's right up here. So this is going to be a quantity 1 plus u squared over 4 minus 1 quantity 1 plus u squared. Don't forget that quantity. Plus 1/2 natural log absolute value of 1 plus u squared and absolute value plus c. And then we make our final substitution. What is u equal to? All the way at the top. There we go. It's equal to tangent. So I'll substitute in the tangent. This is 1 plus tangent of x squared and squared all over 4 minus tangent of x. Oops. Minus 1 plus tangent of x squared plus 1/2 natural log absolute value of 1 plus tan squared of x plus c. Notice this answer does not look like the answer right here. Completely different forms, same answer though, I promise. 1 plus tan squared is actually secant squared. So if you take a look at 1 plus tan squared, this is secant squared squared, or secant to the fourth over 4, minus 1 plus tan squared, which is minus secant squared, plus 1/2 absolute value of secant squared. Now you may say, wait a second, that 1/2, I don't see a 1/2 secant squared here, right? right here. I see the natural log of the secant, but it turns out that that 1/2 just makes a constant multiplier, and that bleeds into the c. So we don't really have to worry too much about that. Let's see, anything else that I want to say? I don't think there's anything else I need to say about that. Yeah, quite a bit going on. Secant. Oh, it's 1/2 secant squared. Sorry. Thank you. This is secant squared right here. The 1/2 is the half power of it. So that is actually secant. Yeah, that does work out. Yep. Perfect. So interesting little things to note here. And by the way, I would keep the absolute values on that natural log, even though you might look at it. Oh, let me finish that statement, then we'll talk about that. I would keep the absolute value on this logarithm, even though if you look at this, you're going to say, well, it's 1 plus and something squared. So that'll never be negative. So I can at least I can remove the absolute values. Well, when you change it out for a secant squared, because that's what this is, a secant squared, and when you drag the 1/2 power up to where it becomes the natural log absolute value of secant squared to the 1/2 power, or secant, you no longer know is that secant positive or negative. So you might as well keep those absolute values on there. Okay. That's what you're kind of always safe with an absolute value. Let's see. Then it was asked, what about doing the u sub for the secant? I specifically used red for that because the secant's not going to work. Well, actually, let me try it. U is equal to secant of x means du would have to steal away a secant tangent. Well, that might work. Well, no. Now remember, if you take a look at our original integral, there was not a secant involved. So, but I do have a power of tangent I can steal away. So, and a dx. So what I'll do is I'll keep the tangent of x dx on the right-hand side there, and I'll divide both sides by secant. So du over secant. Now in this case, this is, well, actually it might work out. Well, yeah, it might work out actually. If you do this, you get the integral of tangent to the 4th, because we've stolen away 1 power of tangent off of this guy right here. The dx will be replaced with a du over secant. But remember, secant is just u. This will work as well. And tangent to the 4th is tangent squared. But tangent, using the Pythagorean identities, tangent is secant squared minus 1. And secant is u. U squared minus 1 squared over u du. And now multiply out that numerator, u to the 4th minus 2u squared plus 1 over u du. And you get down to something else you can integrate. U cubed minus 2u plus 1 over u du. And antiderivative of that, I should be using equal signs throughout, but I just didn't. The antiderivative would be u to the 4th over 4 minus u squared plus natural log absolute value of u plus c, and u was the secant. Secant to the 4th of x over 4 minus secant squared. Really good problem, because you can see one problem leads to 3 avenues to solve out. They all result in the same answer. I kind of wrote large with the red ink, but that's actually a pretty fast method to doing a u sub with the secant. Really nice. And this is kind of the story with integration techniques, is that, and I should label that try number 3. The story with integration techniques is that you can be given one integral, And there might be many methods to evaluate that integral. So just be very aware that there's not one correct method. There are some methods that are better than others, but there's not like one awesomest method that works the best every time. Thank you for forcing me to do the secant, because otherwise I wouldn't have. That's good. So here is a weird case. The integral from 0 to pi of sine squared of 4x cosine to the fourth of 4x. Now remember what I had stated a few pages ago, right here. With trig functions, even powers are very desirable. You would like to make some type of u substitution to force even powers. The problem occurs if you start a an issue occurs if you start a problem where you have a product of trig functions and they're all even powers, because no matter what you do as a u substitution here, one of the powers is going to become odd and you won't be able to exchange it out. Let me write that up above. With sine to the nth power of x times cosine to the nth power of x, if m and n are both even, then a u sub is not going to work. Simply put, the reason why u substitution is not going to work if both powers on these are even is, remember, when you do a u substitution, you're stealing away powers. Let's just say we did u is equal to sine of 4x. Then du would steal away 4 cosine, oops, except you have to write cosine, of 4x dx. And if you did that, your integral, so that implies the integral would become, well, we'd have a u squared, fine. We'd have a 1/4 out front. I don't really care about the constant right now. I'm not that concerned about that. But you'd have a cosine cubed of 4x du. And that's a problem. We stole away a single power of the cosine, and I cannot rewrite a cosine cubed in terms of sine squareds. I just can't do it. So this odd power locks us out. So that's why a u substitution, either a u substitution, if you did u equals cosine, it would be the same thing. It would steal a single power off the sine, and you'd be left with a sine to the first power of x that you would not be able to work with. So in these cases where you have even powers on the sines and the cosines, you're going to have to go to a different technique. Well, the different technique is just that mantra that I say a lot: arithmetic before algebra, algebra before trig, trig before calculus. And we're going to perform some trig before we start into our calculus. Specifically, we're going to reduce some powers here. So in this case, I'll just write it over here in green. In this case, and when I say this case, I mean where they're both even. In this case, with sines and cosines, if both powers are even, we're going to use the half angle identities, or the power reduction formulas. That's a lot to write. Sorry about that. So we're going to just start exchanging these out for power reduction formulas. That's the only thing you can do. You're kind of locked out of integration here. And this ends up being, I chose large powers. They're actually not super large, but they're large enough to be annoying. So I chose large powers because they are annoying. These large powers, to use power reduction on them is a pain, but you're going to have to. That's just how it is. So off to the side, actually, let's go ahead and not ruin our integral. Let's just write the power reduction formulas or the half angle formulas off to the side. We happen to know from the initial review, the first page of this lecture, are two formulas right here. Sine of an angle is plus or minus the square root of 1 minus cosine of the double angle all over 2. That's called the half angle formula. And notice what we were working with were even powers of both the sine and the cosine. So the square roots are going to be gone immediately. So we don't have to really sweat that. So we're going to go ahead and write that over here. I'm going to do the sine first since we actually have just a beautiful sine squared going on. So sine squared of 4x. Now remember, sine is going to be plus or minus the square root of 1 minus cosine of 8x over 2. But because you're squaring it, the square root's gone, so it's just 1 minus the cosine of 8x over 2. Now, that's not a bad move. Also, one other thing you might want to consider here, actually, I'm considering this just because I think that it might be a nicer way to go. Another tactic would be to exchange this sine squared out for a cosine squared. You could do that as well. The end result is going to be the same no matter what you do. But I think I'm going to do that. I'm going to say or sine squared of 4x is the same thing as 1 minus cosine squared of 4x. It's not going to reduce, honestly, the amount of work you do. So you could do the sine squared of 4x equals 1 minus cosine of 8x over 2. You could totally do that. It's not going to actually make a ton of difference. But I think visually, for a lot of people, it's much nicer if they exchange everything out for cosines. So I'm just going to go ahead and do that. I hope you don't mind. So this will be equal to the integral 0 to pi of 1 minus cosine squared of 4x times the cosine to the 4th of 4x dx. If you distribute that through, you're now dealing with the integral of cosine to the 4th of 4x minus cosine to the 6th of 4x dx. There's a little trick you can use here, but I'm not going to yet. And I'll explain the trick when we get to the end and why that trick is somewhat powerful here. But in reality, now that I'm looking at it, the trick is not going to be great until we reduce all the powers anyhow. So the cosine to the 4th and cosine to the 6th. Let's go ahead and exchange those out for their power reduction forms. So I happen to know that cosine squared of 4x would be 1 plus the cosine of 8x over 2. That's the power reduction formula, or the half angle formula squared if you want to do that. So therefore, if you square this, both sides, cosine, that will imply cosine to the 4th of 4x is equal to 1 plus 2 cosine of 8x plus cosine squared of 8x all over 4. I just squared both sides of that equation. And then you also, in this picture, see a cosine to the 6th. So let's go ahead and do a cosine to the 6th. So I'm just going to grab this guy and cube both sides. Let me double check. Yeah, that's cosine to the 6th, cosine to the 4th, cosine to the 6th. Yeah. So I'm going to cube both sides of this guy right here to arrive at cosine to the 6th. when you cube, you'll hear me say it very often. I'll say, I already did this to my Calc 1 students, but I use Pascal's triangle to cube things out very quickly. So if you see me write something like this, and you're wondering how I get it, it's from Pascal's triangle. Cubed 8. Okay. Pascal triangle from your pre-calculus course, very, very powerful for multiplying things out incredibly quickly. All right, so I'm going to trade out all that black ink over there for this new set of green ink. There's a lot of handwriting when you have to use power reduction formulas. Notice I'm going all the way over to the left-hand side of the page because of the amount of writing we're going to have to do. The fourth power of cosine we have right there. So that's, I hope you don't mind, I'm going to write out the 1/4 times 1 plus, actually, no, I'm going to do it this way. It's 1/4 plus 1/2 cosine of 8x. Let's see, plus 1/4 cosine squared of 8x minus. And then we have a whole picture we're going to subtract off. The whole picture we're going to subtract off is all of this stuff right here. It's the cosine of the 6th of 4x. So that's going to be a 1/8 plus 3/8 cosine 8x. Let's see, plus 3/8 cosine squared of 8x. And then plus 1/8 cosine cubed of 8x dx. Notice that the product of these two trig functions here, the product of even powers of sines and cosines, ends up exploding into a massive integral. You have to have the patience to stick with this. It is just one of those integrals that's just a pain. Do not bother evaluating pieces yet. I highly recommend just keeping the integral the way it is and combining things with arithmetic first, like that 1/4 minus 1/8. Well, that's going to be an 1/8. So integral 0 to pi. 2/8 minus an 1/8, which is an 1/8. Let's see, we have a 1/2 cosine of 8x, and we're going to lose 3/8. 1/2 is 4/8 minus 3/8. That's 1/8 cosine of 8x. So really, I'm just trying to make the statement a little more compressed here. As far as the cosine squareds, I have 1/4 of them there, and I'm losing 3/8 of them there. 1/4 is 2/8 minus 3/8 is a negative 1/8 cosine squared. And then finally, minus 1/8 cosine cubed of 8x. Now you can see how involved this is, right? This is pretty crazy. Let me mute while I drink real quick. All right. But we're not near to done. I'm going to break this now apart into 4 different integrals. And that's just a slow little break just so that we have time to really think and see. So it's obviously this is a super easy one here. The fun's going to happen in a moment. Minus 1/8 integral from 0 to pi of cosine squared 8x dx. And the last one, minus 1/8 integral cosine cubed of 8x dx from 0 to pi. The nice thing about having a definite integral rather than an indefinite integral is you can use symmetry. I shouldn't say always. I want to always force you to think about the symmetry of a situation. Well, with 1/8, there's no symmetry. When you integrate when you find the area underneath the curve, y equals 1/8, it's just going to be 1/8 times pi. And that is from a property of integration. The integral from a to b of a constant c dx is just going to be c times b minus a. That's the area underneath the curve, where the curve is just a horizontal line. But the next one, this guy right here, I want you to really think about what a cosine of 8x looks like. Normally, the cosine curve, where do I want to put this? Oh, off to the right. Normally, the cosine curve goes through a full cycle from 0 to 2 pi. That's normally. However, cosine of 8x goes through 8 of those cycles from 0 to 2 pi. In other words, it goes through a full cycle in 2 pi over 8. That amount of time. It goes through a full cycle in that amount of time. Now, imagine that you were to draw this out until you got to pi. You find the area underneath this curve from 0 to pi. Well, somebody tell me right now, if I only found the area underneath the curve from 0 to pi over 4, what is the area underneath this curve from 0 to pi over 4? Yeah, it's 0. You have an area here, you have the same area there, and you have 2 of the negative areas here. And so it becomes 0. And that's just from 0 to pi over 4. But if you have 4 sets of those to get you to pi, all those areas would add up to be 0. So you can use the symmetry. With trig functions, symmetry is beautiful. There's no need for me to evaluate this integral. It will become 0. That's a really nice trick if you're willing to spend the time to recognize that this oscillates 8 times as fast as a normal cosine curve. So it goes through 8 full periods in what we would normally have from 0 to 2 pi. So it goes through 4 full periods from 0 to pi. And each full period that it goes through, the area is going to be 0. So it goes through 4 full periods from 0 to pi. 4 sets of zeros are still 0. Now, the rest of this, we still have a little bit of work to do. Not too much, though. Minus 1/8. The integral of cosine squared, it's supposed to be a square there. The integral of cosine squared. Well, you can't do a u substitution here. Notice the power's already even. If you did any type of u substitution, it would remove a power off that, and that would be bad. But you can use a half angle identity, a power reduction formula. This would be the integral from 0 to pi of 1 plus cosine of 16x over 2. Notice that half angle identity, it's used quite a bit when you start dealing with only even powers of sines and cosines. And that's not true for tangents, by the way, or secants or cosecants or cotangents. It's really just the sines and the cosines that the even powers are just a pain. That's just how it is. If you see an integral of sine to an even power, or an integral of cosine to an even power, or the integral of sine times cosine to an even power, you know you've got some work ahead of you. You have half angle identities to use throughout. If one of them were odd in power, now you're in luck. I can let u equal sine, and its derivative will steal 1 power away from the cosine, leaving me with a cosine to the 8th, and then I can use 1 minus cosine squared equals 1 minus sine squared to finish out the problem. But when they're both even powers, bad news. Just real bad news. There is one exception to that, by the way. I'm not writing the argument because I'm being very sloppy with my notation, but if they were the same even power, you're actually in luck because you can multiply. This is actually something that I should be clean with. Let's suppose that you're handed this integral. And you say, this is the one he warned us about. They're both even powers. It's very true. They're both even powers. I mean, you can't avoid that statement. However, they're both the same even power. That's significantly different. So what I'm going to do is I'm going to multiply the numerator and denominator, not by 2 actually, but by 2 to the 10th, because they're both powers of 10 there. And what you're going to get is this integral. I'll leave the 1 over 2 to the 10th out front. But you'll have the integral of 2 sine of x cosine of x to the 10th dx. And that is a trig identity. That's the sign of the double angle. That's going to be 1 over 1024 integral sine to the 10th power of 2x. And at least that reduces the complexity of the problem. Once they're the same power, you can use a double angle identity. So it's still, you have to use once you use the double angle identity to get from here down to here, you still have to use power reductions, but at least it's not involving 2 trig functions. That's all. Anyhow, that was the exception to that rule. All right, let's go ahead and do this last integral off the back end. Now, there are 2 ways to tackle this. One is just to use the fact that this is basically going to be the cosine, sort of. I'll just say sort of, but it's cosine cubed. It's an odd power cosine. Its cycle goes through 8 full cycles from 0 to 2 pi. So again, this is going to integrate to 0. But if you don't see that right now, and if you're like, I think I can, but I'm not 100% sure, that's okay. You can actually integrate this using yet another u sub. In this case, I would let u equal the sine so that du can force that sine of 8x, so that du can steal away a power of that cosine. So that forces that power on that cosine to be even. So you could totally do that. I don't have an 8 to steal away, so I'm going to go ahead and say this is 1/8 du is equal to cosine of 8x. You will find out that this integral will be 0, but let's just go ahead and go through it in a lengthy process. So if I let u equal sine of 8x, when u is 0, when x is 0, that implies that u is 0. When x is pi, here's a comical thing. When x is pi, well, that means that u is 0 as well. Now, this is actually a dangerous thing. This is one of the rare situations where I would say, do not substitute it completely into the world of u's, because if you did, you would integrate from 0 to 0. And while it is true that this integral will be 0, I'm just letting you know, this type of substitution will ignore certain specific oscillations. You don't want to do that. So I'm not going to transform completely into the world of u's. I'll transform back into the world of x's. This is a rare, very rare case where you do this. So I'm going to write x equals 0 to x equals pi. But everything else I'm going to trade out in the world of u. So let's see, u was sine of 8x. du, well, that 1/8 du, that is. So let me write 1/8 du is going to steal away a single power of the cosine and the dx. So I'll still have a cosine squared of 8x left over. And that, just cleaning things up here, And I forgot my dx on that. That's annoying. Sorry about that. Minus 1/64th. Integral from x equals 0 to x equals pi. Notice how I'm writing that x equals. It's because I didn't want to trade completely into the world of u's on this one because my limits end up being the same, and that may not have been true. So anyway, this cosine squared of 8x is the same thing as 1, I don't need the parenthesis, minus sine squared of 8x. And sine of 8x was u. So that's 1 minus u squared. So cleaning this up, 1 over 8 pi minus 1/16. I'm actually going to go ahead and run this integral very quickly. So that's going to be x, let's see, plus 1/16 sine of 16x. Actually, why am I doing that? It's x from 0 to pi minus 1/16 times, I'm just going to write it this way, integral from 0 to pi of cosine of 16x, because, again, that's a cosine curve cycling. It goes through 16 cycles from 0 to 2 pi. So it goes through 8 cycles from 0 to pi. And remember, each full cycle, the area is 0. It goes 8 cycles, so it's 8 sets of zeros. That is all 0. Or you can evaluate it if you want, but I happen to know from just the geometry of the situation that this here is going to equal 0. Again, because the cosine, just from our picture up here, every full cycle it goes through, the area will zero out. In cases where cosine has an odd power, will always be 0. Let me clean that up and say, in cases that the cosine has an odd power and the argument is an integer, like 8x, or actually it has to be an even integer. So 2, 4, 6, 8, 10, that type of thing. Will it be 0? As long as you're going from like 0 to pi or 0 to 2 pi, yep. Yeah, it will. But I would not memorize that. I'd actually use just logic. Like the logic here is it goes through 16 full cycles from 0 to 2 pi. So it goes through 8 cycles on 0 to pi. And remember, each full cycle, the cosine zeroes out. So it's 8 full cycles of zeros. So that's a really clean way that you can guarantee. Now, if that was, for example, 3, well, it goes through 3 full cycles from 0 to 2 pi. So it goes through 1.5 from 0 to pi. And that's the problem with that. That's why I'm saying you want to be very careful that that number, that you think about it logically. It's not always going to zero out. You have to be kind of logical about it. So be very careful about that. Let's see, minus 1 over 64. Whoops. Let's see, 1 over 64. And this is going to be the integral. Let's see, from x equals 0, I'm going to write it this way, to x equals pi of 1 minus u squared du. Remember, in this case, we had let u equal the sine of 8x. Making some more room. This is going to equal 1 over 8 pi minus 1 over 16 pi. That next part is 0. This is going to be minus 1 over 64. The antiderivative will be u minus u cubed over 3. And we're going to evaluate this from x equals 0 to x equals pi. And so therefore, I'm going to trade back into the world of x, which is going to be nice. Let's see, 1/8 minus 1/16 is actually 1/16. So it's 1/16 pi minus 1 over 64. And then u, remember, our substitution up above was sine of 8x. So this is going to be sine of 8x minus sine cubed of 8x all over 3 from 0 to pi. Sine of pi, 8 pi, is going to be 0. Sine of 0 is going to be 0. So that whole back end disappears. And our final answer is pi over 16. That's a big problem, right? So I wanted to showcase kind of the rest of the integral there, but in reality, I could have said exactly what Raj was asking about, which is when we dealt with, and I'm going to highlight this because it's a really, really like, I'm going to highlight it right here. I'm going to highlight this because it's really hard to see in all this handwriting. But this right here, this is technically not just the cosine. It's obviously the cosine cubed. However, because it's an odd power of cosine, it still exhibits the same behavior as a regular cosine. So it still does this. Okay. It goes through 8 cycles on 0 to 2 pi. So it goes through 4 cycles on 0 to pi. If I go through 4 of these full cycles, even though it's a cube, not a cosine, but a cosine cubed, it turns out all the cube is doing is it's making it slightly steeper at points, but it doesn't change where it crosses the x-axis at all. It doesn't change where it gets to the highest points or the lowest points. So the areas will still cancel. So I could have avoided all that mathematics and said, oh, this is just 4 cycles of a cosine essentially, and they will zero out. So you could do that. The reason why I finished it out the way I did is because what if this was not a definite integral, but instead an indefinite integral? I wanted to showcase what you would do. You'd make a u sub to steal away an odd power and finish out that problem. This is a lot of work. Watching this is not enough. Doing this is incredibly important. This is a very, very good example of why writing down the lecture notes as we move forward is very important, because watching this, you'll go, oh, yeah. But then if you win, you see this in a homework, you're going to be like, oh, wait, how does that go? So your hand to paper is very important here. Yeah. Can you please show the same even power part? You mean like, can I just re-explain that? So if they have the same even power, right? So if you have the integral of sine to the second, let's say to the 20th, and cosine to the 18th, in that case, you must do power reduction. Also, let's just say it was sine to the 20th. Same thing. So when you start with even powers on sines and cosines, or sines, when you have just an integral involving sines or cosines, or sines and cosines, but everything's even power, you're out of luck. That's the worst case scenario. You have to do power reduction. There's only one small exception, is when they're the same power. So sine to the 4th of x, cosine to the 4th of x dx. When they're the same power, you still kind of have to do it, but you can massage the problem a little bit by multiplying the numerator and denominator by 2 to the 4th, in this case because it's the 4th power of sine and cosine. It's still going to lead to power reduction, so I don't want to give you the illusion that you're not going to have to use it. But if I leave that 1 over 2 to the 4th out front and bring in the 2 to the 4th into the integral, I would have 2 sine of x cosine of x. That's the 4th power dx, but that's a trig identity. That's supposed to be a 16. Sorry about that. That's the sine of 2x being raised to the 4th power. Unfortunately, it's still being raised to a 4th power, so you still have to do power reduction at that point. But it's not a power reduction on a sine to the 4th times a cosine to the 4th. Now it's just a power reduction on sine to the 4th. It's a little less complex, so you still have to do a power reduction there. Yeah, no matter what, even powers are, you want to arrive at even powers if you can, um, but high even powers end up being a little bit of a pain. So very high even powers actually are incredible pain. Notice this problem has started, by the way, because I'm just thinking about that statement I just made. When a problem starts with even powers, that's when you have a concern. However, if you were to start a problem that didn't have even powers, let me find one. Yeah, like this. Here's a problem that didn't start with even powers. After a U sub, we get to even powers. But from that point forward, because you made a U sub, you could rewrite that even power in terms of your U sub, and then it becomes a polynomial. But that's the only time when even powers work to your benefit, is if you used a U sub to arrive at them. Would I want to use a trig identity for matching odd powers? So if they were both odd powers, so this is where the author goes into his little discussion about, even, odd, odd, even, right? That's what he talks about, all those three cases. If they're odd powers, you might be in luck. So here is a case of odd powers. And odd powers are actually really nice. If you have both odd powers, at least for secants and tangents, you're in incredible luck. Think about the substitutions that can be made here. You have two choices. Either u is equal to secant, or u is equal to the tangent. Now, think about the ramifications of a substitution before you perform the substitution. For example, if you let u equal the tangent, it would steal away 2 powers of the secant, because that's the derivative of the tangent. It's secant squared. And you'd be left with a secant to the 7th, and that is no good. You could technically convert everything to sines and cosines. Absolutely. That'll be a little bit of a long haul, though. So I'm not going to do that here. But I'm going to just tell you that in this case, du would steal away secant squared of x dx. And this implies left with odd power on secant. And that's no good. I don't want to do that. So instead, if you just think about the derivative of the secant, it steals away a power of the secant and a power of the tangent. Yep. That's an x there. And so our integral, if you did u equals secant, you're going to steal away 1 power of secant, highlight that, and 1 power of tangent and the dx. So let me go at least start there. I'm going to steal away a power of the secant, a power of the tangent. So I have a secant to the 8th of x and a tangent to the 4th of x. And the dx gets stolen away as well. And that gets stolen away all for a du. But remember, our substitution was u equals secant. So that secant to the 8th is actually u to the 8th. And having an even power on that tangent is incredibly helpful here, because tangent squared is secant squared minus 1. But remember, we don't have a tangent squared. We have a tangent to the 4th. So I double that up. And remember, secant is u. So this becomes, again, another polynomial. U to the 8th times u squared minus 1 squared du. And really, ultimately, you want to have polynomials. Polynomials are fast to integrate. So this type of substitution, really, really very powerful. And I'll distribute through u to the 12th minus 2u to the 10th plus u to the 8th du. And now I'll just do the antiderivatives. So that'd be 1/13th u to the 13th minus 2/11, u to the 11th, plus 1/9, u to the 9th, plus c, because it's an indefinite integral, and then substitute in what u was, which is secant. So this ends up being a lot faster because you had a really nice way, a really nice substitution that made all powers even. So the secant 13th of x minus 2/11 secant to the 11th of x plus 1/9 secant to the 9th of x plus c. There you go. So the previous problem really showcases like the worst case scenario. That is there's no other scenario that is worse than having even powers, starting with even powers on sines and cosines. There's nothing worse than that. And that's why I have it in my lecture, is because I don't want you to have to face that in the homework without having seen it. Because it is nice. It's a mess. Yeah. I don't know what you mean by matching odd powers. 100%. No, you just have one of them on the homework. Yeah. I think there's only one, because they're not super common, but it is important that you know how to deal with those. Otherwise, these ones are the most common, where you can do a u substitution to then quickly integrate. If you had a sine to the 9th times a cosine to the 9th, let's just say, dx, you could do either u sub. So I'd let u equal sine, du would steal away cosine dx, and now you're to this. U is sine, so that's u to the 9th. I steal away a power of cosine, so now I have u to the, cosine to the 8th du. And now I'd exchange that cosine to the 8th for a cosine squared to the 4th. And cosine squared is 1 minus sine squared. So you see what happens if you're facing, okay. Oh, no. Well, I suppose you could. I see what you're saying. So the question is, what could you do that same trick, double angle identity for that? 2 to the 9th over 2 to the 9th, sine to the 9th, cosine to the 9th, dx would be 1 over 2 to the 9th integral of 2 sine cosine to the 9th dx. And no, I wouldn't actually. 1 over 512 integral sine of to the 9th of 2x dx. Now, I mean, you're going to have the same amount of work, because here you're going to say, well, let u equal cosine of x, of 2x, in fact, and then du will steal away a negative 1/2 sine of 2x dx, which is the same. We do have 1/2 to steal away, but not a negative. So this can be a negative, our integral, that is, be a negative 1 over 256. And then we'll have a sine to the 8th of 2x du. Okay. And that sine to the 8th, I'd have to then do the same thing that I was just doing, which is write this as the 4th power of sine squared. So it's the same amount of work. That would be 1 minus cosine squared, and that'd be 1 minus u squared to the 4th. So it's the same amount of work as if you had just from the get-go just done a regular sine substitution. It's going to be the same amount of work. These are things that you can kind of investigate as you go through, because there's a lot of possibilities. You can see that I have 14 pages of examples, which I shouldn't, honestly. But the reason why is because there's so many different exceptions that occur. And so you have to kind of be prepared to pivot at any given moment, to change your tactics. But yeah, if you did the double angle identity for the sine there, you'd have the same amount of work. It would still work, but it'd just be the same amount of work. Now, these are just, I call them extra substitution examples because all you're doing here is extra substitutions. I'm not going to do the full ones. I'm just going to showcase the idea here. Notice it's a mixture of sines to powers and cotangents to powers. Sines play well with cosines, but they don't play well with cotangents or cosecant. Well, cosecants they do, but they don't play well with like really cotangent really is the one that doesn't play well with. So what you can do here is rewrite it in terms of sines and cosines, which was a tactic that was mentioned by Raj a few minutes ago for something else. So you write this as sine squared times cosine cubed of x over sine cubed of x dx. Obviously, powers will cancel. And in this case, you would just let u equal sine. So that's just to let you know, you're going to run into some examples. Don't think you have to get extra super fancy. It is always an option to exchange things out for sines and cosines. It might not always work, but it is always an option. Okay. So if you let u equal sine here, it would steal 1 power of cosine from the numerator and you have a cosine squared. And then that would be a really ideal situation because then you get this integral u cosine squared of x du because we stole 1 power off the cosine, and then cosine squared is 1 minus sine squared, which is 1 minus u squared over u du, and then you do division. That'll be natural log absolute value of u minus u squared over 2 plus c, and then you reinsert what u was, which was a sine. So you can see some of these are going to be very fast. Obviously, it's fast for me just because, I've been doing this for a long time, but you're going to get to a point where you speed through examples because some of them are just set up to be easy to integrate. So again, reminder, if you have an integral of a product of trig functions, if it's sines and cosines, or really in any case, you'd like to get things down to even powers. If they're not compatible functions, like sine is compatible with the cosine, but it's not compatible with the cotangent, try changing everything to sines and cosines instead. Here's a fun example. This one should scream at you what you need to do, but if it doesn't, then I can guide a little bit here. So the fact that it's not a product of trig functions, but instead a product of two completely different types of functions tells me I'm probably going to have to use by parts. So different types of functions implies by parts. However, remember how by parts works. You choose something to integrate and something to differentiate. In this case, you cannot integrate immediately the tangent squared. You can integrate x, but if you choose to integrate x, it will just get ugly. In other words, it'll become an x squared over 2 when you integrate that, and you'll have to differentiate the tangent squared. That'd be a 2 tangent times secant squared. It just gets really, really ugly. Luckily, you're dealing with trigonometric functions, or a trig function. So do a little bit of trig before you start into your calculus. Tangent squared is the same thing as secant squared minus 1. And you may think that doesn't get you anywhere, but it does. Because when you split this integral, Not only do you get one integral that you can evaluate, the minus integral of x dx, but now you're facing an integral, again, a product of two different types of functions, but I can integrate secant squared. Whereas the original problem, I couldn't integrate tangent squared, but secant squared, totally you can integrate. So in blue ink, I'm going to let u equal x here, and dv, the piece I integrate, be secant squared of x dx. Well, du is going to be dx, and v is the antiderivative of the secant squared, which is a tangent. A really, really, really nice problem now. Remember, by parts is u times v, so that's x times tangent of x, minus the integral of v du, tangent of x dx. And then remember, we still have this minus the integral of x, which is x squared over 2. Technically, there would be a plus c, but I'm not done with my integral, so we'll just go ahead and leave it like this. And you should recognize our integral of tangent of x, going back to page 1, just to remind you, the integral of tangent of x, oops, it's page 2, sorry. It's the natural log absolute value of secant, or you're more than welcome just to do a u sub to arrive at that. But that's what we have here. Let me hop back to our problem. It's minus the natural log absolute value of secant. And now minus x squared over 2, and then plus the constant of integration. That's supposed to be an x there. Sorry about that. That's supposed to be a minus. So a problem that looked to be pretty gnarly to begin with, a simple trig identity breaks it into very nice integrals. So be prepared for stuff like that. You're going to see stuff like that all over the place. This is integration techniques is just a bunch of stuff all at once. It's like a hodgepodge of integrals that you have to practice. Practice makes you better with this stuff. Not watching me do it, but actually doing this and going through and trying as many problems as you can. You'll get really good with it. It's a game. It's a really cool little puzzle style game. I'm going to advance the slide here, or a page, I guess. Okay, I included this one in here only because I had to. If I have an integral of a product of trig functions, specifically the sine and the cosine, and they're of different angles, this and this, different angular arguments, believe it or not, you're in luck. You're in luck because you can use the product of sum formulas. This is the only time you're ever going to use those product of sum formulas, is if you have the product of, say, like in this case, cosine of 5x times the sine of not 5x, sine of 7x, right? In that case, that's a very specific case, but in that case, you get to go back to page 1 in these notes and note here that if you have a product of sine and cosine, where's my highlighter? Hidden. There it is. For the product of sine and cosine, it's 1/2 the sine of the difference of the angles plus the sine of the sum of the angles. So that's what I'm going to do here. It's just a rare circumstance. So let's go back down. Sine is written first, so go back down to here. I'm going to first write it in the proper order, just so that I match up everything. Sine of 7x, cosine of 5x dx. And then I'm going to trade it out using our sum to product, or sorry, product to sum identity. It's going to be the integral of 1/2 the sine of the difference of the angles. And I can't remember because I don't actually expect anybody to memorize these, plus sine of the difference of the angles plus sine of the sum of the angles. So if it was an exam or a quiz, I'd give you the formulas if you needed them, by the way, because, again, I don't even memorize them. And from this point forward, we go ahead and integrate, right? So this is 1/2. The antiderivative of sine of 2x is 1/2 sine of, is negative 1/2 cosine of 2x. And the antiderivative sine of 12x is, again, negative 1/12 cosine of 12x. And remember, there's a plus c off the back end. And I would probably factor out a half or distribute the half. Doesn't really matter. Kind of the same idea. So negative 1/4 cosine of 2x minus 1/24 cosine of 12x plus c. And the question was, why can't we sum the same angle? What do you mean, why can't we sum the same angle? Do you mean, are you saying, why can't we write this as sine of 2x plus 5x? Cosine of 5x? Because that's how the formula is derived. I'm not sure if that's what you mean, huh? Yeah, I say it's good news when angles are different. Oh, yeah, when angles are different, it's good news because then you can just use product of sum formula. If they're the same angle, cosine of 5x, sine of 5x, that's good news too. Because I'll just let u equal the sine, and it steals away the cosine. So if they're the same angles here, then you're also in luck. Yeah. It's good news both ways, right? So, but compare it to all the previous examples. These are fast when you can use the product of sum formulas. Although, to be honest with you, not super common. Again, it's kind of the obscure sets of problems. We only have 3 minutes left, and I just want to see, okay, here's something super fast. So in the last 3 minutes, if you're asked to integrate something like this, really look for identities. Look at this and say, ask yourself, is this similar to something you've seen before? Is this structure, the square root of 1 plus cosine of 2x, is that similar to something you've seen before? Curious if anybody, okay, good. What does it sort of look like? Power reduction, good. Okay, it is, What is missing is a 2 in its denominator. But guess what you can do? You can force a 2 in its denominator. You could say, hey, that's like the square root of 1 plus the cosine of 2x over the square root of 2, but I'll have to offset that division by the square root of 2 using a multiplication by the square root of 2. In other words, I multiply top and bottom by square root of 2. When you do that, you get this. That's the square root of 1 plus cosine of the double angle over 2. And we happen to know that is just a fancy language for cosine of x. So root 2 integral 0 to pi over 6 of cosine of x dx. It's a very, very cool problem. The antiderivative of cosine obviously is a sine. And sine of pi over 6 is a half. So this ends up being root 2 over 2. I'm missing my equal signs because I was just kind of barreling through. Sorry about that. But a very, very good style to always stop for a moment, even though I'm barreling through, stop for a moment and go, is that something familiar? And it totally is. That's very, very familiar structure. And you can force it into the actual true power reduction or half angle identity by just multiplying top and bottom by the square root of 2. All right. So we are knocking at the end of the day. We have only 3 examples left in this section, and then we start section 7.3, which is honestly everybody's favorite section out of the integration techniques. So on Friday, we will go into the integration techniques of trig substitutions, actually is what it's called. Otherwise, I'll be back in 10 minutes for office hours.